All right, welcome to the last session of the RISE camp. So this is going to be the security session. You're going to see how to use our security artifact Wave. Wave provides a decentralized framework for authorization. So you can think of it as the security framework that underlies the different projects in the RISE lab, the different systems. It basically it connects them together in a way that only authorized systems or entities will make certain actions. So it connects different people together, devices, sensors, but as well systems and services. So Mike here is going to give you a short introduction about the system, and then he's going to lead the tutorial. Have fun.
Hi, good afternoon, everyone. Right, so I'm going to be giving this talk about Wave. This has been joint work with a bunch of students under Professor Color and also Professor Edepopa. So in a nutshell, as Raluca alluded to, Wave connects sensors, actuators, controllers, drivers, apps, people. It's basically the glue that connects various different services and pieces of larger systems. And you can think of it as acting as a secure, decentralized bus. You have devices attached to this bus, you have sensors, services, and it allows all of these things to communicate in a completely authorized manner. The syndication mechanism here that we're offering is a publish-subscribe. It's fairly common in IoT patterns for devices to use publish-subscribe buses. And importantly, this decentralized bus operates with no central authorities whatsoever. So as a little overview of Wave, essentially it provides a democratized authentication and authorization system. What we mean by this is anyone can grant permissions. They can do so without communicating with any grantee or with any authority, so it's non-interactive. Anyone can verify any permissions non-interactively, so there's a proof of authorization in the system that can be verified non-interactively. And every action that takes place carries a complete proof of its authorization. And on top of this, we provide fully authorized syndication, parallel syndication, with no trust of the routers or brokers. We provide transparent, publicly auditable permissions, but if desired, we also allow private permissions. And the whole system is attack resistant and highly durable. So the principle in the system is the Wave entity. If you're trying to picture, put this alongside traditional systems you may be familiar with, this may be, an email address or a username, the thing that is typically associated with permissions. In actuality, it's a key pair that is used for signing. It's a signing and a verifying key, and it's used for signing things. And it's identified by its public key, its verifying key, which is this long 32-byte sequence of characters. Now, there are many security problems associated with trying to work with these unwieldy sequences of characters. I could switch a couple of these characters around, and no one in the audience would actually really recognize that it had changed. So we also provide a globally unique immutable alias for this. So for example, that sequence of characters is bound to the sequence of characters Mike19. And because it's immutable, it is as secure as using the public key itself. So throughout the talk today, you will see many places where we have these short human-readable sequences of characters. These are these aliases, and at times they refer to these full public keys. And this entity represents the holder of the signing key. Similarly to how, if you think about it, a username really represents whoever has the password. In this case, an entity represents whoever has the signing key, and it could be an IoT device, it could be a participant, or a service. Then permissions are granted on resources. So you can contrast this with URLs or file paths in other systems. So within Wave, all of our services are composed of multiple resources here. So you can see a thermostat may have a resource that allows you to interact with a set point, remotely change the set point. A door lock may allow you to change the state of the lock or read the state of the lock. And there can be read-only resources as well. So your utility, your electric provider, may advertise the current price of electricity or things like that as a resource that people can consume. And these resources are grouped within namespaces. Now, in traditional authorization systems, there is a notion of a root of permissions. So when I install an LDAP server, as the administrator of that server, I can arbitrarily create permissions. I am the root from which permissions flow. In a traditional Unix file system permissions, the root user is that sort of root of permissions. And this is actually intrinsic. There has to be some root of permissions, and in our case, this is the namespace. So every resource appears in a namespace, and that namespace is actually a public key of an entity that created the namespace, or its alias. So you can see here Alice Home on the right. You can imagine that as being equivalent to the public key of the entity Alice Home, and then the rest of the resource. And the namespace entity has full permissions on all resources within the namespace. It's intrinsic. It cannot be revoked. And what's important about this is that the URI alone, simply by discovering a resource or coming across a URI, is enough to know which entity has intrinsic permissions to this. So you can imagine if I receive a message here, there's this envelope, and on the outside it says that this was signed by Alice Home, and there's a valid signature there, and Alice Home is an alias for the public key, so I have everything I need to verify the signature right there. And I see that the message is for the resource, Alice Home HVAC thermostat set point. I know that that message is immediately valid. Without consulting any external entities, I have all of the information I need to know that this action is authorized. Of course, it's not very useful if the only entities that are authorized to interact with resources in a namespace are the ones that created it. So you need a way to expand this out. And in our case, this is a delegation of trust. So it's similar to assuming a role or joining a POSIX group in other systems. Basically, a delegation of trust confers some permissions from one entity to another. And we know that the namespace entity has complete permissions, so as that entity grants to other entities and they in turn further delegate it, we get this expansion of trust. And in the delegation of trust object is a standalone object. It contains the grantor and the grantee's public keys, what permissions are being conferred, what resources those permissions can be applied to, and some metadata like, is it allowed to be further delegated, when does it expire, who's allowed to revoke it, things like that. And of course, this whole object is signed by the grantor. So if we receive this object, we can immediately tell if it's well-formed and valid. So a typical delegation of trust might be Alice saying, you can publish to the door-lock resource to someone else. Now, this naturally forms a global graph. The start of any portion of this graph would be the namespace, and as it delegates to other entities, each of these keys here denoting, this blue keys denoting a different entity, as it delegates to each of these, it forms this graph. And to prove that an action is authorized, it is sufficient to show that there is a path in this global graph that leads from the namespace entity to the entity doing the proving, which is the orange circled entity on the right-hand side here. And of course, each one of the links that is traversed by this path must grant a superset of the permissions being proven, so that the intersection of all of these links is greater than or equal to what the proof is claiming. Now, this proof of authorization is the fundamental concept in Wave. Every action that is taken, whether that be consuming a resource or publishing to a resource, which is actually a proxy for causing some real-world action to take place, everything carries this objective proof. And we say it's objective because, for reasons that will become obvious later, when a prover forms this proof, they can know that no honest party would refute it. Once I form this proof and I attach it along with my action, I know that every honest party will agree with this proof and my action will take place. And this property is very important for non-interactive systems, because if I take an action, I want to know that the other side will believe it's authorized. Typically, you might have some kind of session where the two are communicating and it can say, no, it wasn't authorized, try these things. But we want this ability to have non-interactive interactions, basically simplex communication. So it's important for our proof of authorization to be objective. And as I mentioned earlier, no communication is required to verify this proof. On the syndication side, I'll give a brief synopsis of this. So imagine a case where you have an application and you have a device on the right-hand side, and they're wanting to communicate. Both of them have access to an agent. In the case of an IoT device, this agent process may be embedded in the device. It may be externally and communicated with over a secure link. But everyone has access to an agent, and this agent is responsible for performing all of the cryptographic operations that Wave relies on, so that you can really design your applications in any language, and your devices can be constrained. Those agents communicate via a router, which forwards messages, and that router is bound to a namespace. So when the application wants to publish to a particular resource, say under Alice Home's namespace, it resolves that namespace public key to the router that it needs to communicate with, and we'll see how that happens later, sends that message along with the proof that the action is authorized to the router. The router will verify that proof and drop it if it is not verified, and forward on to any agents that are subscribing to that resource. They in turn will also verify the proof, and that's important because we don't actually trust the router. So if the router is malevolent, you could imagine it doesn't verify proofs and just forwards things along. So the recipients also verify it, but in the case that the router is honest, we gain some good DDoS properties, because basically illegitimate traffic or unauthorized traffic doesn't reach the end device. So kind of an overview of this, the device forms this message with the proof. That gets verified by the router, and the proof is basically compared against the namespace, because the proof should be a path from the namespace specified in the resources to the sender that signed the message, and then it gets sent to the applications, which do the same thing. So where are we so far? Well, we've constructed a system that performs authorization and syndication, and it does this using entity and .objects, and it has some useful properties already. So we actually don't have any ordering constraints. Because of the way that the dot graph is traversed and created, I can grant permissions that I don't yet have, and that will appear as an unconnected edge in the global graph. And then when I receive those permissions later, that edge could potentially become part of a path and become useful. So this no ordering constraint is very useful for deployments in IoT devices. You have the ability to repair permissions when things become expired without having to redelegate the whole chain. You have the ability to deploy devices and commission their keys before the higher level entities are granted permissions and so on. We also have a system that can subsume existing authorization patterns. So we can perform role-based authentication with this, we can perform group-based authentication with this. But the system is not yet actually functional. We require a few properties from these objects in order for the system to actually function and be sound. So firstly, we've kind of glossed over availability. We assume that everybody has access to these objects. When an entity is created or a delegation of trust is created, everyone must have access to this. And more strongly, we require that everyone has the same view of which objects exist and which don't. Otherwise, we lose the objectivity of the proof. If I form some proof that uses a set of objects, and you're not aware of some of those objects, then you could disagree with my proof. And more importantly, if there is a revocation, and people have differing views of which revocations exist, then really your revocations aren't worth very much, which is the case of revocations in TLS in the web today. They're kind of very hacked in at the moment, and they can't really be relied upon. And of course, the system, if we're going to use this as a core authorization system, it will be actively attacked. So the whole system has to be resistant to attack. So kind of giving away a little bit how we achieve these properties, I'm going to jump into a quick introduction to blockchains. So the way blockchains work is you have a set of mutations of state, each one called a block. And each subsequent block references the previous one. So block state 2 has the hash of state 1 in it, so that they're kind of linked. And what happens is people propose changes to these states, transactions that change the states, and they kind of get broadcast. And miners will take a set of those transactions and put them into a block, seal it, which involves some work, and put that out into the public as, I propose this as the next block. Now, naturally, there could be multiple people proposing the next block, and those blocks could be different. So as pictured here, there is state 3 and 3 prime proposed by 2 different parties as the next block in the chain. What will happen is that some of the people proposing blocks will pick one of those blocks and append extra state onto it. And append extra state onto it. And because each of these links are expensive, the system automatically adjusts. I'm referring particularly to the Ethereum chain here. The system automatically adjusts so that each sealing a block takes about 15 seconds to do, irrespective of how many people are actually trying to solve the problem and seal the blocks. Because these links are expensive, we have the property that the more blocks are appended after a block, the higher the odds that that block will remain around forever. So we refer to these additional blocks as confirmations of a block. And the reason is, imagine some attacker comes along and decides that there was some state in S3 that they want to revert. So if, for example, there was a revocation of a key they happen to possess and want to use as part of an attack. So they proposed S3 prime as not including that revocation because they want that object to disappear. So then they go and they work and they put on S4 prime, they put on S5 prime. and they get all the way up to S7. But the problem is those links took a long time to make. So in the time that they made those links, everyone else will have put more links onto the legitimate path. And so the guarantee that we have is as long as the attacker has less hash power, less than 50% of the hash power, they won't be able to overtake the main chain. So that's why we consider something as being secure once we have enough confirmations, because the probability of someone being able to successfully make something disappear once it's in the chain is inversely proportional to how many additional blocks are on the end there. Now this is, cramming a ton of blockchain stuff into a handful of slides, but it'll become important to us in the demo later because you'll actually witness some of this. The system automatically analyzes the chain and ensures that it only tells you an action is complete when it knows that an action is immutable and in the global chain state. So a basic summary is really that these blockchains provide a global synchronized ledger of state. And once state is in the ledger with some confirmations, it can be relied upon to stay there. Also importantly, there is no authority in this chain. There's a bunch of parties all acting of their own accord, trying to add states onto the end of the chain, but there's no company that owns it, or at least for public chains, there's no company that owns it. There's no one who has authority to rewrite history or do anything with it. So it's really the primitive that allows you to make an authority-free global system to do coordination with strong consistency at a global scale without having anyone in charge. Now, in newer blockchain technologies, there's also this notion of a smart contract. And basically, our transactions, instead of just being the transfer of money as it was originally in Bitcoin, they're more like invocations of a function in a contract. And this contract is written out. It's basically like a small program that's written out, and the program is stored in the blockchain. And the transaction refers to this function, and it can run and mutate global variables. Now, you can't really think of this as having significant processing power because despite the fact that there may be hundreds of thousands of people engaged in this, they're all having to repeat the same computation. But what is important is that I can put logic in this function that says, I will accept this transaction if it obeys the following rules. So you can kind of get very complex consistency guarantees, even though it's this kind of global decentralized system. And these functions that mutate these global variables, those get stored into the blockchain state database that everyone has a synchronized view of. So the answer to our problem posed earlier, how do we get these additional properties, lies in these blockchain smart contracts. And we have 4 contracts that Wave relies upon. The first is Wave object inspection. So when I have an entity object or a dot object, this contract is able to verify the signatures, verify that everything is well formed, so that if someone tries to publish a delegation of trust where the signature is faked, that the contract can say, no, I will not allow this state into the database. This is quite useful because it means that the only state that gets stored there is potentially valid objects. Then we have the registry, and the registry stores all of our entity public information, which is basically the public key and the expiry metadata. We also have the storage of the delegations of trust, and these are all indexed so that you can access these objects efficiently. I kind of glossed over this earlier, but the way that you resolve a namespace, a URI, taking its namespace and resolving that to an actual server you speak to, a traditional method would be to use DNS, but it turns out DNS is actually not particularly reliable. There's a lot of poison attacks you can do, and if you use DNSSEC, then you're trusting some external authority. So we have a contract that stores these mappings, both from the namespace to the router public key that will route it, and then also that router's public key and its IP address. So it's a bit like DNS, but without any central authorities. And then finally, we have a contract that stores these aliases. So this is how we can guarantee that I can choose some human-readable sequence of characters to represent a public key, and I know that it's immutable and globally unique. It's stored in a blockchain smart contract. And it turns out this technique is surprisingly effective. We obtain the properties we set out to get. We have availability through the blockchain state dissemination mechanism. We have consistency in that everyone will have the same view of the blockchain, or they will be aware of the fact that they're partitioned. So you could imagine if I was running a blockchain agent and I lost connection to the internet, I don't have the same view of the state as everyone else, But I do know that I'm partitioned because I know that the last block I have is old. And when we go into the notebook later, you will see that the first thing we do is we check, are we up to date with the latest global state? And because the system is a fintech system that has billions of dollars of market capitalization, it is attack resistant. They spent a bunch of time making sure that the engineering of the system is resistant to attack. And basically that links any attacks that you would do on the system with financial costs. So it becomes very expensive physically in terms of physical money to attack the system. So we obtain all of these properties, but we obtain them without the use of a central authority. And if you think about it, that's completely unlike any authorization system you think of. Things like OAuth rely on some federated identity provider. Active domains rely on some server. POSIX, any existing system, we can provide strong consistency without a central authority. So it's pretty exciting work. It's this global authority-free authorization system which allows very fine-grained delegation. It uses a public authority-free blockchain, which is a new development. There have been some proposals to do something similar to this using private consortium chains, which basically means the whole blockchain is encrypted and you pre-share all the secrets. But the problem there is really there is an authority. Whichever company is running that, maybe that's Chase, they actually can interact with the chain and override parameters in it. And although we don't get into this later, I encourage you to go and look at some of our papers later, but we also managed to do this, we also managed to maintain resource privacy. So the system is fully implemented, and it's been running for more than a year now. I think we're at about 450 days. We've used this across tens of buildings, thousands of devices, billions of data points have been sent across here. And what we're going to do today is take a bit of a slice out of what we have used this system for. So my research group works a lot in buildings. We do operating systems for buildings, smart city kind of stuff, IoT. And one typical service in this space is a controller. And what a controller does is it consumes a bunch of things, such as sensor data within a building, a model of how the building should operate, and thermal parameters, takes some sensor data from, say, outside weather, and some control parameters from the building operator, and it uses all of that to actuate the building. So control the thermostats, control rooftop units, variable air volume boxes, things like that, space heaters. Basically, it operates your building. And what we're trying to do here is build a controller that can operate at a large scale across multiple buildings just to save energy. And we're going to do a much simpler version of that. So our sensor will be a light switch, which you can imagine as being a Boolean sensor, on or off. And we're going to, and there is also a light bulb, which is our actuation that we can turn on and off. And what we have set up for you already is a namespace where these services already exist. So the light switch already has a persistent running service that consumes it and converts that into a boss wave resource or a wave resource. And we have on the light side a driver that listens to that resource and actuates the light on and off. But it's important to note that the light switch knows nothing about the light, and the light knows nothing about the switch. There is no binding between these. What we're going to do is create that binding. So at the start of it, the namespace entity already exists, and the permissions for these services already exist. They can interact with the namespace and bind to those resources. And you will create your own entity to interact with the system. And obviously, after you've created that entity, you won't have any permissions to interact with this. You're going to then request permissions to interact with the namespace, and a delegation of trust will be made to you. Then you're going to create a new entity for a controller. In Wave, it's generally good practice to create new entities for every kind of concept. So if it's a service, it gets its own entity so that you can have fine-grained revocation, fine-grained management of permissions. It's often, in other things, if you sign up for, ohm hour, demand response, energy savings, you give them your PG&E username and password, right? I mean, it's the worst security model. We're really trying to build something that allows you to delegate permissions without conflating your identity. I'm not giving my private key to someone else, but I can still independently grant them permissions. So you're going to create an entity for your controller and grant it the subset of permissions that it needs to function. And it's then going to use the light switch sensor data and actuate the light bulb. So that's the first half of the tutorial that we're going to do. And then the second half is you're going to build a more advanced controller that consumes third-party information. So there is a completely separate namespace that provides some weather information, and you're going to consume that resource in your controller and use that to influence how you actuate the lights. So let's jump right into this. If you open up the notebooks, you should still have your login information from earlier. And if you don't, you can put up your hand and some folks will go around and help you. And inside the notebook, there is a wave folder. And inside there is a wave IPython notebook. So the first thing we're going to do is verify our environment. So whenever you're writing a controller that's interacting with Wave or any application or service, it communicates via an agent. And we have set up an agent running for you in this notebook environment. And this first line that we run here will connect to that agent and verify its status. So when you look at these fields, it'll tell you how many peers that's connected to. So the way blockchains work is they typically communicate with a bunch of peers to learn about latest updates onto the block. Cool. Can everyone run this first cell, this wave status, okay? And so it'll also tell you what the current block is. And if you haven't connected to the internet for a while, you've been partitioned, it'll also tell you which block it knows about, but is still busy catching up to. And it will tell you the age of its state. And so this is pretty important, because this is how we know when we're partitioned. If you have been partitioned for a while and the age of your state is maybe an hour, you have a choice to make. Do you continue to accept messages that have proofs that may refer to things that have been revoked? Or do you not interact with people because you know that you're partitioned? You know, it's a policy that gets chosen on a per service level, and it's normally got to do with how important the actuation would be. So if you're going to be actuating something you can't reverse, then maybe you want to make sure that you have the latest view of the state. But it's a useful property that we don't have in many other systems. And this difficulty here is a parameter of the blockchain. It's basically how many people are actively mining on it, and how hard the block ceiling problem is. So the first action we're going to take here is to create your entity. So that, you know, in order for you to interact with the system, you have to first create that entity. So in this cell here, when you create an entity, you can attach some metadata to it. So you can attach some contact information and a descriptive message, and also an expiry. So fill in your name here, and you'll see why that becomes useful later. As you start interacting with other people, this information can help them identify keys. So I'm going to start running that, and you should see some output that looks like this. It creates your entity, and you immediately know what your public key is. It also saves it to a file for you to use later. And then it publishes the object to the blockchain. And by default, the blockchain interaction parameters here wait for 2 confirmation blocks. And this is basically what I referred to earlier. The state might be available in the blockchain immediately, but if you're going to take some action on this, you want to know that this is irreversible, that even if there were currently an attack busy being mounted on the blockchain, that no one could reverse the action that you've taken. And so we wait for extra confirmations, extra weight to be appended on after our block before we consider the action as done. So this can take a varying amount of time. It was actually fairly quick here. The block sealing time is probabilistic, so sometimes it can take a minute or so, but this only happens when you're interacting with the permission control plane, basically creating new entities or delegating permissions. None of this waiting happens in the data plane when you're actually sending messages. So everyone should basically get to this point here where you can see that all objects are published. So some people... What does the actual error say?
Not everyone have the ms.ent.
Why?
I don't know, but...
Oh, did they restart the containers?
Maybe. So they need to rerun the...
Oh.
But they usually you don't tell people to run the dot / restart message.
No, but what? But
this is on the home directory.
But why did it start for me if everyone's running the same container?
Some people.
Okay. It seems like there was some infrastructure patches that happened. So apparently we need to rerun the script. So, I guess we can do it from here. So try doing this. It's actually in this directory. So where's J? I mean, I don't need to run this. Well, I mean, I've already got this one. Okay, so if it did already run for you, then you will get this message that I have. Basically, this is for the light and the switch. It's getting the keys so that everyone has unique keys. So try, if you were getting errors, try again and see what happens. I might. Is anyone still having problems? Okay. So let's just okay. So who has not got their entity created? Okay, so once your entity has been created, you now need to actually get access to the namespace. So just creating an entity, you now appear in this global graph as a single point, but there's no edges. You don't have access to anything except resources that happen to start with your public key. So each of you is on a separate namespace. You have your own, light and switch. And if you try and get access to resources on this namespace, you will see that there is no chains found. A chain is basically a path through the graph that shows that you have permissions. So we have no permissions. We now want to ask for permissions. So if we inspect our entity file, you can see a bunch of parameters for your entity. This VK line here, this is your public key. And these are kind of cryptocurrency balances. You don't really need to worry about that for this tutorial. But this is your public key here. We want to create an alias so that your name is easy to type and convey to people. So if you copy your public key here, you come down to this make alias cell, you can choose an alias for your public key. So it has to be globally unique. So pick something that people are unlikely to have chosen. So I'm going to go for rc.michael. And then paste in your public key here, and it will create this globally immutable alias. And similarly to the creation of the entity, it only tells you that it's complete once it knows that the action is irreversible and unattackable.
So echo namespace, the chain failed.
Yeah, did they change the container? Why are none of these variables set?
Can you just start clean slate for everybody? What's this?
Where's Jay?
Who's the account?
Yeah,
Jay.
this is Jay. Yeah.
It is environment variable. So maybe the namespace is not the namespace we are creating the SS. Where did this wave start file come from?
Well, I mean, I don't know why they changed the container again.
Let's try how to fix that. So does we keep a namespace or
hang on to this.
Or something?
Were the containers restarted?
Not since.
So we're having some technical difficulties with the tutorial environment. There's supposed to be a script that runs at the beginning that sets a bunch of variables like $namespace here. And it seems that script has only run on some people's machines. So as a show of hands, how many people are actually having problems like where this isn't there? That's a lot of. We might need to relaunch this or something.
generate a bunch of dummy accounts that we can give to people to have them log in with a new session.
Okay, yeah.
And then, meanwhile, we will try to figure out.
Did it fix it? Does it fix it if you run that?
Oh, yeah. Can you just run the short script inside? Yeah.
Like this one?
I think it's dot.
No, I think that would do too many things. You want to run your the wave start script.
But the wave start script
and
does
then,
not contain the exports. The exports are in RiseCamp start.
Yeah, it's going to be too late at this point because you're trying to set it on the parent process basically.
Yeah.
You're making a child process that has that environment.
Yeah, it won't set the variable.
So, but you can do like os.setEnd to change the process environment and then all child processes.
But if that environment variable wasn't set, then like were the keys copied? Like what else is missing?
That's a good point.
So maybe create new accounts so we can hand out new accounts to people.
Yeah,
cool.
and let's also get an IP of broken.
Sure. I think Ruluka's one is broken. So what we're going to do is we're going to, for those people that are having problems with the containers, we're just going to give you a new account, and you can sign in, and then that one will work. So typically, when you work with Wave, you have these services running on your system, and you know this kind of stuff it doesn't happen as this. It's kind of easy. The tricky part here is we have one environment with a bunch of different tutorials in it, and they kind of interact with each other. I don't know why. Scripts in here.
Okay, let's get everybody to count off and increase sequentially so we can give people.
Okay, sure. Okay, so everyone who needs a new account, can you hold up your hand? And I'm going to give each of you a number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Anyone else? Okay. 14? 15. Sure.
Visit risecamp.tech/login.
All right, so everyone who's having a problem, go back to your sign-in page, so risecamp.tech/login, and
user and a number at risecamp.tech.
So say your number was 16, you would be like that, user 16 at risecamp.tech.
Sorry, no, it's example.com.
At example.com. Like that. And the password will be the same as the one that you used last time. How many did you create? Okay, so that should work for people. Did a quick test. I switched over to a new one. It seems to be okay for me. No, it should be fine. I don't think you need.
People are still having issues in the new accounts. Same thing.
Like, how did they test?
They ran the command and they got the same.
Which command though? Because they need to run through all of them.
The one with I'll check the ran through all of them.
So if you want to double check that the new container is working fine, you can just add a line here that says echo $namespace, and you should get some line at the bottom here that looks like this.
The counter did overflow.
No, but it hasn't though, because then I would have a higher number here. I made 300, right? 126. So
could there have been something like some of the containers starting to reboot before you reset? I think it started the push at like 8 a.m. 8:30, something like that.
I don't think so.
Okay, let's see what's all about.
Oh, we can do that. Maybe. Found something?
No, I just had one of the affected machines.
Someone was running. Do you have a new number? What's the maximum number we can use?
20 so far?
20?
Yeah,
what's the maximum number for you?
You can go up to 19. So I think we have 15. So you can choose between 15 and 19. Yeah. Sure. We can go get them laptops. Sure. So if you have switched to a new notebook, you'll need to execute those steps. So you start off by making your entity here again. You can pick the same comments there and running that so that the object can publish. Then you can see running this cell again, and then once you've done that, you can run the cell. You'll see that you have no permissions. And we were basically down here at the alias. So what you have to do is from your entity output here, you copy this public key. So this is basically the content of the alias. This is what you want to bind the alias to. And you copy that, and you go down to make alias, and you fill in some unique alias. So pick something unique that you suspect will not have been used. Without spaces, it will be useful later. So just something like you would call a variable name, and then paste in your key here and run this. And now this will create and bind the alias. So once you have your alias record created, you can now get access to the namespace. So typically the way that this works in real life is you would go and you would communicate with someone who has access to a namespace. So like your boss or the owner of the building that you're deploying a device into, or whatever someone in that namespace. We've scripted an interaction here where it's kind of like a toy example. You communicate with someone. So type in your alias here and run this get access script. And basically, it's like going to someone who owns that namespace and saying, hey, can I have access to your namespace? This is what my entity is. And they can now create a delegation of trust to you that grants access to the namespace in question. So I'm busy being granted complete access to this namespace here. Because they reused something. I can fix that. But they shouldn't have done that. Okay, so, you found something?
From get entity, there's some kind of exception. I'm not sure I see, this is std out, this is std in. Not sure I'm seeing anything about what the specific message is. But, exception then.
So can you find Gabe? That guy in the jacket, I think. Thanks. So when you go over to, you can now go over to this extra notebook. There's a notebook here. You can click this link that allows you to inspect a namespace and look at the graph of permissions within that namespace. So I run this, and this is what the permissions look like at the start of the namespace. So there was the namespace authority, and it's granted some permission to a light and to a switch. It is busy being resolved. I don't. It's happening in the background. If you know what number. Well, if you know what number their namespace is, I can do them first.
But otherwise, they just wait and it works.
Yeah, eventually.
So I can give you the number for the namespace.
Yeah.
Someone cannot find an S.end. And it's not in the parent folder either.
Yeah, that's the same problem as the.
Other people have the same problem.
No, that's the script wasn't running properly.
So you have to have another. So I start with 17.
Or go to Gabe and you can rerun get entity. 151.
151.
Okay.
One moment.
Okay.
So they need to run, if they get a new container, they should run RiseCamp start, not wave start?
It should be wave start. They shouldn't even have to run that, but the get entity pi is crashing.
Yeah. Are you sure the entity server is still up and running?
Yes.
Okay. Yeah, because it's, because I have the JSON, I get the JSON as a response, and I call get message to get the key message out of it, and that's returning none. And then it fails the rest of the script.
I mean, yeah.
So like, I have a guy with a new container who ran wave start, but his namespace environment variable still is on.
Yeah, because that won't work because you're running a script and it's the child process, so it can't set the.
Okay. Sorry to follow that. Okay.
He still doesn't have the funding at 151. How long does he have to wait?
It should be basically done
In like a few minutes.
in like by now it's probably already done. So he can when you rerun this command, oh yeah, so it should be done by now. Okay, so for those following along, so who has run this get access script? Cool. So now you should have some permissions. You can inspect the permissions that were just created. So in the output here, it will say there was a delegation of trust that was created, and this is the hash. So if you copy this hash and you paste it into this cell over here, it will tell you a little bit more about this delegation of trust. So it will tell you who created it, who it's to, when it expires, and it will also tell you, is it valid in the global registry and so on. Now, if we go and we rebuild the chain to try and check if we have permissions to interact with the namespace, we find a proof. So this object that gets printed here is the proof that I'm authorized on the namespace. So the proof in this case actually consists of a single delegation of trust from this entity to me. And if I go across to that other notebook, the examine namespace notebook, and I rerun this, you can see that in the namespace, there is now a third link, and that links to my entity. So in your notebook, there already exists a few entities that were there to start off with. So the light, and you can see that the light already has permission. This is building a proof that the light can access resources that start with s.light. And you can also see that similarly the switch exists, and there is already a proof that allows the switch to access those resources. We're now going to create a virtual light in the notebook so that you can interact with it. So this light here is a standalone little process that is listening to the wave resources and can be controlled via those authorized wave resources. So we can create a client to interact with those resources in the notebook. So here we're going to create a client, and we can publish a message to the light to turn it on. Now what's important to note here is that this was a global message interacting with the resource. We're not like controlling a picture in a notebook cell. This is a global resource. In fact, if you were to, you can interact with the people next to you, control their lights in their notebooks if they grant you permissions. We're also going to create a switch and start making our service. So let's create an entity for the service. Yeah. Yeah, it's worth noting that the time that you wait for these blockchain operations, this is only because we're enforcing a minimum level of security, and they're also fairly rare. They only happen when you create entities and do delegations of trust. Things like signing, creating proofs, verifying proofs, those all happen in about 2 milliseconds. These operations are a little slower. While we're waiting for that, I'm also going to queue up creating an alias for the service. And the way that IPython works, it'll run this cell once this operation is finished. Oh, sure. As a quick check, is anyone still having problems with their account? Because Jay can probably help you out.
So they managed to create the same alias assigned to two public keys.
No, you can only create one.
It is.
It doesn't. You can submit multiple transactions, but only one will appear in the blockchain.
It sees them in the graph. It sees them in the graph in that program, in that figure.
Grant the same alias to multiple entities?
He managed to grant the same alias to different verification keys.
Oh, I mean, you can do that if you put like a homograph attack, right? It can't be the exact same sequence of bytes.
It's the same sequence of bytes.
I promise you.
Go to him and say.
So now that we have our alias, our service entity, like us when we first created it, doesn't have any permissions. We need to grant it the permissions to consume the sensor readings, basically the light, and the permissions to control. So we're going to create two delegations of trust here from our entity, which was granted permissions by the namespace, so we're further delegating these permissions. We're going to grant it to the service entity, but instead of granting it all of the permissions on the namespace, we're only going to allow it to publish to a specific resource here. Similarly, we're going to grant to allow it to consume just a specific resource as well. What's Ruluka, what's the namespace number? Okay, so my second delegation of trust. Also, you can normally do a lot of these in parallel, so the throughput is normally much higher. But in the IPython notebook, everything is very serialized. So.
I'm throwing your stuff though. So the last two deploys are.
Oh, oh.
Pixels after that. Okay, the last two are the same.
I hate copying things out of.
Yeah.
the last two dots? You can't alias dots. Okay. Right. So my dots have probably finished propagating, so I can go and I can look and I can build both of those proofs. So those proofs exist to the server, to the controller. I'm going to come across here and you don't need to modify this. I modified this earlier. So you can see in the graph of my namespace, there is a new entity here, and it has two dots granted to it that allow it to interact with the services. So now we can start our persistent process. Now typically this gets run in an environment that handles restarts, like you would run it inside a Docker container and things like that. We're just going to run it in a cell in our notebook, but if you come along here and you run this cell, it's going to create a background process that is our controller that consumes the switch and will actuate the light. So if we actually go and we can duplicate the same controls down here. Here's our light and here's our switch. When we interact with these now and we click these, you can see that the switch is controlling the light. Now this is, this cell here knows nothing about this cell. In fact, if you were to go and modify this code to talk to the person next to you, as we will do shortly, it will actuate them as well over the internet securely without using any central authority. So this gets us into part 2, which is basically federation. You may think that what we've shown so far is overkill for connecting a light switch and a light on the same computer, and you're right. But the real strength of the system is that it enforces authorization among multiple parties without any of those parties trusting each other, or without having any central authority as a mediator. So pair up with someone next to you. One of you will be the controller that is going to be issuing control commands, and the other one is going to be the client. We're going to do a little controller as a service setup. So the controllers, you need to have your alias handy so that you can give them to the clients, because the clients need to give you permission. And the clients are going to run a command that looks a bit like this. So I don't have anyone to pair up with. Okay, so you need to run this command, rc17 dot what, sorry? 88. So you need to run this command here. But okay. Huh?
Insufficient funds, not enough gas to.
Because people have been running cells multiple times. Anyway, so the clients, so are you going to be the controller or the client? Okay. You can be the controller. So I am going to grant permission to access your namespace to my controller. Now, I don't actually have permission to your namespace yet, but that's okay, because remember, you can grant permissions out of order. Now, you need to grant permission to me to interact with the namespace. So my controller alias, I need to actually go and look up what my controller alias was. Service alias Michael, this one here. So copy this text, or write it down. And then down here, you need to execute this command. Make dot from your entity to my controller's entity, which will look like that, on your namespace.
Okay, so basically if they're out, you have to transfer it to their namespace?
Do you know what number they are?
Yeah, 156.
Okay, that'll be in the next block. Okay, so you granted it? Cool. Nice. So I am now going to have a controller here that publishes to your light, consuming my switch. So I'm going to run this, and let's see if the permissions have propagated yet. I'm going to go up to my switch, and you'll see, okay, they haven't propagated yet. It takes a little bit longer. So you can see it says I don't have permission. And if we wait a little bit, I'm going to actually go and examine your namespace over here. So this is what your namespace looks like. You can see that my entity doesn't show up here yet. Yeah, that's good. Here we go. This delegation of trust has shown up in your namespace, so you can see that I now have permission to publish to the lights in your namespace, or at least my service does. Now, you should see, does your, oh, I might need to rerun my controller, hang on. So now you should see that your light is turning on and off as I turn it on. And you should also see that your light will actually say who turned it off. I actually have two controllers running here, so I'm controlling my own lights at the same time. But so what's going on here is that my notebook here is forming a message that says turn on the light and attaching a proof, and it's sending it through the router, and it's arriving at the service in his notebook. His notebook is verifying it. Now, neither of us trust each other more than just that single delegation of trust, and neither of us consult any third-party authorizing services. So there was no Google doing OAuth or anything like that. He didn't consult my LDAP servers. I didn't consult his. That message was entirely self-standing and self-proving. So if anyone's having trouble doing that with the person next to you, you can put up your hand. Gabe can go around and kind of help you. And for those who are feeling a little adventurous, and you've already done all of this, you can go and do the next part here, which is to integrate some additional information. So I'm going to, instead of just doing a plain switch as a service, I'm going to integrate some cloud cover, and I'm going to use an external signal to control his namespace. So there is an existing signal here that we can actually go and take a look at. If you take this resource, everyone has access to this resource. So if we could, for example, do a new cell here. Actually, I'll do it over here. You can see that it puts out a feed that looks a bit like this. Every second, it tells you what the current cloud cover is, and this changes fairly frequently. So over here, I'm going to change my controller to use this signal to control the lights. So you should see that as the cloud cover falls below 70%, your lights turn off on your screen. And as it goes above 70%, your lights should turn on. So are they off right now? Is it off? And now it should turn on now. There you go. So now we have a service that is consuming resources from multiple domains without any of those domains, having a central trusted party, and every message can be verified independently. And the final step, for those who want to try it out, is exploring revocation. So I'm going to get you to run this command. You granted me a delegation of trust earlier, and that had a hash. So when you go up here, copy that hash that you had for that delegation, and go and paste it at the bottom here. Oops, not that. I didn't actually copy it. Yeah, so run that, and you should see that my service should spontaneously stop working as soon as that object is published into the chain. Over here. So unlike other objects, like entities, revocations don't need as many confirmations. They need confirmations to be sure that they're not going to disappear, but they don't need confirmations to take effect. So they're pretty fast. You can see that immediately my service has stopped working because it lost its access while it was busy trying to publish. Could not build a proof. No access chain found. And if we go back and we look at your graph, we rerun this here. I need to stop this from running. I actually don't really know how that stops. We can see that the link to me has now disappeared. In fact, we can actually look at all of the links, including revoked links, and you can see there used to be a link here to me, but it has since been revoked. Now, this is pretty cool because normally the way revocations are implemented is either by opportunistically trying to make them available in a DHT or something like that, or by hard-coding revocation lists in multiple pieces of software. We have a system here that allows arbitrary revocation without any central storage of revocation lists. technical difficulties aside. Yes, so the interesting thing about building a completely authority-free system is that we're not authorities over it. So any of you can go out and use it, and there's nothing we could do to stop you even if we wanted to. So the code is all released. It's on GitHub. I think I had that up here. And we also have APIs for a couple of different languages. So we have a Golang API is our primary one. We also have a Python API, a Java API, Android API, and I think a Lua API. Scala API, that's true. That's true. Ah,